Welcome, everyone. I am Helen Spainhour here with Neve Research and Code 41. We are so glad you joined us today for the webinar, Building Fraud Detection Using Transactional Analytics. I have just a couple of housekeeping items. As you probably know, everyone will be muted except the presenters. And then at the end, if you have any questions, if you will just submit those, we will get to those once we finish the webinar. So without any further delay, let's meet our panelists for today. Colin, if you'll get started and just introduce yourself.
I'm Colin McNaughton. I head up engineering here at Neve Research. I've spent my career in middleware and infrastructure and integration. So I've got a long history with distributed computing. I've been with Neve for many years now, and it's a fun place to work. I'm happy to be presenting today. Igor, would you like to introduce yourself?
Hello, my name is Igor Mihaljevic. I am a lead engineer at Code 41, and we specialize in high performance computing systems and use in real-time ad bidding, online gaming, social network analysis, big data stream processing.
Thanks. And we also have Lynn on the call. She'll be serving as our moderator today. You there, Lynn?
I am. Thank you, everybody. And thanks again for joining us. So as we get started this morning, just a quick overview about the folks that are here, the organizations that are represented. Code 41 is a partner that we've worked with on several engagements, and they specialize in building data and very low latency transactional types of applications. Those of you that have ever looked into some of the webinars we've done in the past, you've probably noticed that Code 41 actually has done a couple in the trading spaces as well, some of the exchange spaces. So that's a little bit about Code 41. So we're welcome. It's always a pleasure to work with them. And then also, Colin and myself are from Neve Research. We're a company that's headquartered in the Silicon Valley. We are really the authors of a product called the X Platform. And that is a memory-oriented application platform. So for a lot of the things that we'll do today, we'll try to use it to kind of give you an idea of the types of performance and how easy it is to really build these transactional, analytical, multi-agent types of applications. And our customer base is primarily in the Fortune 500. So I just wanted, so that's kind of who we are. And now as we get started, I think really what is kind of important for today is to kind of think about the fact that as e-commerce is getting so much more popular, and as a result of everybody flocking to do a lot more transactions electronically, we've also seen a huge growth in the whole area of fraud. So it's easy to figure out that as more e-commerce happens, and the faster the fraud is, the faster the response has to happen. Otherwise, you pretty much end up losing all of your, what would have been your revenue, into the form of fraud that you're paying back. So as the growth kind of happens and the response needs to get faster, we're finding customers that we're working with are doing several different types of detection strategies and incorporating the transaction. One of the key things they always worry about is the impact on the user, the false positives, not making the transaction any slower, whether it's happening online or actually happening at a checkout with an electronic payment or credit card payment. And then, of course, the other one is just the cost. You know, the whole fraud area kind of eats into your bottom line. So you don't want to spend more trying to prevent it than you would have if you just let it go. So that's always a factor for these people. So those are kind of some of the things that we really see as being some of the drivers and the challenges right now in working in the fraud detection space. So as we get started, I'm going to actually ask you, Colin, maybe to kind of pick up with what you really see as the issues and the types of architectures.
Sure. So, like Lynn was saying, in fraud detection, in transaction processing in general, accuracy is really important, right? There's a real drain on the business if you miss a fraudulent transaction, and there's a heavy sort of impact on customers if you falsely detect fraud. So it's not particularly good customer sentiment if a valid transaction is declined. And as transaction volumes continue to increase, it's also important that we keep up with the speed of response time. No one wants to wait for authorizations to go through. So in terms of achieving better accuracy in fraud detection, as transaction processors begin to leverage newer technologies to achieve better accuracy, pull in more data, the systems, transaction processing systems, are getting more and more complex. So we have greater sort of data sources available to us. Like we started seeing people leverage IoT type streams on customers' location data to do better fraud detection. And of course, there's a greater demand to look at transaction processing data, the operational data, to do better analysis or analytical processing, transaction histories to detect patterns in fraud. So we want to use things like machine learning, artificial intelligence, and all these are sort of very data hungry technologies that are analytically intensive. And what's sort of tricky is that analytical loads on operational transaction data tend to, or at least traditionally have tended to block more update intensive transactional operation processing. And of course, since we want to keep transaction processing streams fast, high throughput, and low latency, there are certain challenges there. So we've got ourselves facing a much more complex ecosystem, which is putting more infrastructure strain on transaction processing systems. So what people are doing, there are several sort of key technologies we've kind of identified that are helping transaction processors. I think first I'd like to start with microservices. So as complexity increases, breaking applications down into smaller business functions is really key to getting a handle on complexity as we're adopting new technologies. So you get the somewhat unsurprising agility benefits of breaking a more monolithic architecture down into a service-oriented one, in that the smaller functional units can act more agilely, operate at their own release cadences, and hit delivery targets with lower risk. And that lower risk in turn drives more innovation, because businesses aren't as afraid to try out new things. I can take a smaller project and try to integrate a new technology without risk to the overall transaction processing ecosystem. So these multi-agent architectures really help us sort of break down the problem and get a handle on complexity, allow us to innovate a lot faster. But one of the other things about microservices that's a bit more subtle is that one of the tenets of a microservice architecture is that state or an application's data is private to that service. So the only way you can update that data is via messaging or some sort of well-formed communication pattern with that service. And one of the subtle things about that is that tends to reduce update contention in our data fabrics. So if we have only a single process or fewer processes updating data, we're not going to have as much write contention on our data stores. So that operational data, we can ingest more data. And that in turn gives rise to being able to adopt more sort of stream processing frameworks and streaming analytics. So as opposed to the more traditional architectures of batch processing of data into some sort of back-end database and doing long-running analysis to generate business insight, we're seeing instead that we're bringing into the transaction processing plane the ability to ingest these streams and do sort of continuous queries, continuous analytics on that. And a lot of that's sort of enabled by the ability to actually ingest this data more. So a big part of doing that is breaking the application out into these smaller pieces. And finally, I was talking before about the real desire to get analytical insight into operational data. So in a credit card processing context, this is customers' transaction histories to make better assessments about the risk of a particular transaction. So we've seen a push more towards HTAP, hybrid transaction analytical processing. What that's really about is, while microservices allow you to ingest more data by reducing write contention, these new HTAP techniques typically leverage in-memory computing to allow you to do analytical processing in parallel with update-intensive loads. So this is really giving people a lot more visibility into the data that's in motion in the transaction plane to make smart decisions. So Lynn, I think that's kind of my take on sort of the state of technology and some of the approaches people are trying to use. I hope that kind of answered your question there.
That did. But before we let you off the hook, let me ask you a question about the X platform, and basically how does that fit into this transactional microservices, microagent architecture, and what's the advantage there?
Well, the X platform actually is a single platform that addresses a lot of sort of the technological advantages of some of the approaches I'm just talking about. So we're a memory-oriented platform, and that allows us to do some of the hybrid transactional analytical processing by bringing all application state into memory. That allows you to, in the transaction processors themselves, see recent transaction data without any sort of cost in calling out to a data grid. So your data is right there. We're built from the ground up as a multi-agent architecture. So we play very well in a microservices context. And the fact that we're sort of focus-oriented applications means that we're very focused on asynchronicity and streaming. So the platform is really encompasses a lot of these kind of concepts in one sort of easy to use package. So when you look at X, we're very much focused on making it simple for developers to write these multi-agent applications. And to achieve this, there are sort of two things with the X platform. So we're very much geared towards multi-agency. So we like the idea of breaking down applications into small components. So you wire small components around their state and sort of chain them together through messaging to collaborate. But the key feature of X is that we allow you as an application developer to treat memory as if it were durable. So the plain old Java objects that you're operating on in your business logic handlers, you can work with that state, that RAM, as if it's persistent. And we can get maybe a little later to how we actually do that. The other really key thing is that from a messaging standpoint, we give you fire and forget semantics. So what we mean by that is when you send a message, you don't need to worry about the disposition of that message downstream. We're going to guarantee that that makes it to any other agent that's interested in receiving it. So the combination of the platform in one sort of package handling both your application state and messaging allows us to do some really impressive things from a performance standpoint in terms of keeping data and messaging in motion. So X applications really are pipelined all the way through without any blocking semantics. That gives us the ability to operate very high performance. So without application developers thinking too much about it, you can achieve really high performance and easy scalability. So let me just take you through kind of the responsibility breakdown of what the platform does, what an application developer would do. So firstly, the platform gives you modeling tools that allows you to model both your state and messaging. So this is stuff that's managed by the platform. So built into your tool set, we're going to give you the capability to just generate plain old Java objects you as a developer can then focus on writing your business logic that's going to use these. You're going to declare message handlers based on the messages you model. And while you process those messages, you'll update state and send some outbound messages. So you as a developer, your business logic is very much concerned just with working with plain Java objects and no sort of infrastructure bleed into that code. So we're sort of very focused, I would say, on keeping the developer experience kind of infrastructure free. And that makes it a bit easier to find Java talent that can focus on the business problem you have at hand. So under the covers, the X runtime is going to take care of all the sort of non-functional stuff, the infrastructure concerns with your application. So transactional messaging, message connection establishment, how things are persisted, how things scale out horizontally, and how, in the event of failures, we can ensure that no inbound messages are lost, no state changes are lost, no outbound messages are lost. That's sort of the responsibility of the platform. And it's a big priority not to have that bleed into application code. So I won't spend too much time on this slide. This kind of shows what an X application would look like, but I think Igor might give us a look at some code from the application he's written. What I want to impress upon people here is that really there's just any handler you write is very simple. You're just working with objects. You don't have to do any persistence. You annotate event handlers on message types, update some state, send outbound messages. The platform takes care of the rest. So just to drive home, it's a productive environment. You essentially model messages in state, write your business logic, and feed deployment configuration into the platform. And that's it. You're kind of off to the races. Finally, just before I pass back to you, Lynn, I might as well give a bird's eye view of the platform as a whole. So the types of applications I've been talking about, we call micro apps, which is sort of a spin on microservices that just kind of gives the sort of feel that these are streaming applications. But we also have a framework called Eagle that allows you to do more request reply oriented orchestration. So oftentimes we'll see people using Eagle microservices at the front end and then kicking that back into a more asynchronous processing chain in the back end. And I thought I'd introduce a little bit of our deployment stack. So we have a tool called Robin that gives you sort of scripting and allows you to hook into a lot of deployment frameworks. And we have a Lumino front end, which gives you dashboarding, real-time visibility, allows you to export stats from your application and visualize them, as well as doing lifecycle management on applications. So that was a very rapid introduction to the X platform, but I want people to get to hear a bit from Igor about his experience building sort of credit card processing on the platform. So if anyone has any questions, I know I went through that very quickly. Very happy to take those later. Otherwise, Lynn, let me pass back to you.
Great, thank you, Colin. So Igor, since Colin's kind of teed you up now to show us your work, if you don't mind, maybe you could walk us through kind of what this looked like when you were doing it, what some of the challenges were you saw, and kind of how you managed to get this in transaction analytics done.
Okay, thank you. So I will talk about one of our high-performance computing projects done for credit card payment systems for fraud detection in real time. So the requirements that we had were to have fraud detection done on the in-flight transaction. We want to plan for very high transaction rate that would make the system applicable from relatively speaking, smaller clients such as card issuing bank, up to the most demanding clients at the level of card association networks such as Visa. We want very low latency in the range of maybe tens of milliseconds. We also want the possibility to eventually evolve this system into a full payment processing solution, not just dealing with fraud detection aspect of credit card processing. The system would have to be plugged into an existing payment processing and banking software. It must work nicely with something that is already in use and not replace it or impose any kind of big architectural change. Since we are planning for use of advanced fraud detection algorithms, it's one of the popular research problems in computer science. We want nice integration with native libraries, since we may want to use hardware acceleration using graphics cards and FPGAs with OpenCL and good API support. So to give a very high level overview of what the fraud detection is, fraud detection is analysis of what about the incoming transaction is unusual compared to other transaction, what stands out, what deviates in some way. So it's a combination of a number of manual checks and some kind of statistical analysis, such as naive Bayesian classification, or even more advanced statistical models, such as one obtained through training of a neural network. And the problem of real-time fraud detection is that it's a problem of analysis stuck into a problem of processing. Processing intersection is looking into a row, and it's short running, and fraud detection analysis is looking into a column, so it's long running. So processing intersection may be asking, does this card number really belong to this card holder, or does the card holder have enough balance on their debit account to deduct the purchase amount? And fraud analysis is asking, is this amount unusual compared to other 300 payments this card holder made, or has this card holder ever bought anything from this state or country before, or even how does this card holder's spending habits compare to hundreds of thousands of other card holders? So we clearly cannot traverse the entire data set of our system for each incoming transaction. And we can avoid doing that with mentioned statistical models, where we are constantly calculating averages and variances and median mean values. But we also cannot fully avoid accessing and traversing at least some of the data. Simplest example of that would be checking geolocation. For instance, is it really possible that one credit card was used once on an East Coast state in US and then 20 minutes later on the West Coast state? So it's probably not possible. And to do that check, you would need to look into card holders' transaction payment history and see, for instance, the last time this card was used, where this happened. So hence, the near real-time fraud detection is a hybrid transaction analysis kind of a problem. And the reason we partnered with Neve on this one is to build it on X platform is because our experience with one of the previous ad exchange projects and the requirements in this project on very low latency and high rate and messaging being the easiest way to integrate with an existing system. So what we will show here is one portion of our fraud detection system that I have extracted from our project. I would say from the start that project is functionally not complete for the demo that we will give, but still sufficient to demonstrate to anyone involved in these kind of problematics the key aspects of implementing real-time fraud detection. And since we are donating the code to open source, we want a project that anyone can easily run without specialized machine learning libraries and graphics cards and drivers and any other dependencies that may be difficult to set up. So the actual algorithms of the fraud detection are simulated, but we still don't show just the message flow. We will actually impose some workload on our applications to simulate them actually performing analysis and spending some time doing it. We will show that in more details later. So I want to show how to organize a complex payment processing or fraud detection system using microservices architecture. How to do it when we have a rich data model, and if you're coming from relation database aspect, there's in microservice architecture you cannot have thousands or 100,000s of tables related. You have small micro applications that manage only a portion of the data from your data model. I also want to show how to scale for storage capacity and computation power, and how to achieve that with very low latency, and how to handle failures without loss of service using guaranteed and exactly once message delivery system. So our app will show a simple workflow. There's an incoming credit card authorization request. We will want to identify the card holder. We might want to identify the merchant, and then using the data from card holder on their previous transaction history, and using maybe some data on merchant, the store where the transaction was committed, we would like to perform some analysis and then also perform another step in analysis involving a statistical model that is obtained on all the card holders that we have in our system, and then give it some score on possibility of fraud, and then send the authorization request. So this is how the application system looks on built on X platform. We will have a performance driver application which would simulate authorization request for us, so that we can simulate the load with which system would work. And this is the starting point of authorization requests, and then from left to right, the authorization request would land in credit card master, where we would try to identify credit card number and see if there is credit card holder with that number, and then we would add this data to authorization request, forward it further, then go into merchant master and see for merchant ID in the authorization request if we have some merchant data, like location of the store where purchase was done, and then forward further into credit card holder master, and this is where we have retained the full year of payment history for a credit card holder. And this is the first step of analysis, where we are doing a personal data analysis. One of the examples being the one that I given before, where we would then use the merchant store location and compare that, for instance, with the last purchase on that card for this card holder. And then we would go into forward it further into next micro app, and this application would do a statistical analysis on based on all the data that we have in our system. We would build a statistical model from that, and then we would perform analysis based on that. And this is the place where you might want to integrate machine learning algorithms such as neural network or other kind of statistical analysis. This is a place where you can integrate with native libraries and use hardware acceleration using graphics cards, for instance. So fraud analyzer would demonstrate how you would do that, and the merchant master would, for instance, demonstrate how would you enrich the authorization request with additional data and then gather all the data that you need to start the analysis, and how to do it with micro applications. So I would like to give a demonstration of the system, the project that we have built. I'm going to go first into a deployed system that that was built on the architecture that I showed in the slides, and then later we will take a look into the code to see how it works. So I have a system brought up and running. Each of the 4 applications that we shown previously is sharded, and also we have a backup instance of each running. We used 2 servers to do it, and we have run a warm-up of the system. So we have 2 shards. They are nearly perfectly balanced, almost exactly half of the state, and handling half of the throughput. So we have around 200,000 merchants. We have 40,000 card holders. We have 80,000 cards. So about each card holder has around 2 cards, and they have, as I said, a year of transaction history. Around 350 transactions is held for each card holder, and the starting number of authorizations is 2,001,000. So I will run. I'm going to run driver to send new authorization requests. Let's say that we are going to send 1 million requests, and the rate that we can have using our 2 servers would be around 7,500. Okay, so it has started running. We have so the rate went up to 7,500, and let's see. So we have a latency somewhere under 2 milliseconds. So as we can see, the applications are processing requests in microseconds. The flow adds up and finally ends somewhere around 2 milliseconds, let's say under 5 milliseconds. And the other thing that to notice is that these 2 applications, Card Master and Card Merchant Master, are working in tens of microseconds, and the Card Holder Master and Fraud Analyzer are working in hundreds. We imposed this, as I said previously, we are simulating the actual analysis. So there is a sleep cycle in cardholder master and in fraud analyzer applications. They cannot go below. They will work at least at 100 microsecond latency. And what I can do now maybe is, let's say this is primary. What I can do here is kill one of the instances, and what we have done now, since merchant is one of the shards is going to handle half of the authorization request load, we could be breaking here now. We could be losing half of the load, but since we have guaranteed exactly once delivery, what happened is that the backup instance that we have had on another server, on the server one, took over. So there is no message loss. Now we can see some delay that can go up to 1 second at the time of failover when backup instance is taking over, but we don't actually even we cannot even notice that we had a failover. So the system keeps running, and we started with 2,001,000 messages and ended at 3,001,000 messages. So even though that one of the machines went offline, no message was lost, and we didn't even have a delay that could be expected at the time of failover. So to sum up, we had around 200,000 merchants and 40,000 cardholders. We had 80 cards. We had 2 partitions for each application, and we were running everything on just 2 servers. We had one shard running on one server, and then another shard is running on another server, and the backup instance was running on the opposite server for each of the apps. And we managed to pull 7,500 authorizations per second and have high availability, and we managed to do it with latency under 5 milliseconds, perfectly handling failovers. And maybe it's worth noting that this is running on commodity servers, I think, from 2012, and our messaging broker is in a virtual machine. So having 7,500 authorizations per second that in the environment that we have here is really impressive. For instance, Visa Net handles around 30,000 transactions per second at days such as Black Friday, when they have the highest traffic, and we managed to simulate about 1/4 of that traffic with 2 machines. And so let's see the simplified diagram of how the flow works. So we have authorization requests, and the authorization request has So the authorization request has very little data. It has merchant ID, store ID, post terminal ID, any other identifiers. And we have a very rich data model. We want to get any kind of information that we can obtain to improve our analysis of current transactions. So one way to organize message flow is a daisy chain, where you would pass messages from one app to another until out the other end comes the response. And within each application, you would add some bit of data that you want. So when we land in card master, we would append card holder ID, and when we then land in merchant master, we would append any merchant data such as street address of the store, and then we'll pass it into cardholder master, and then cardholder master would use the cardholder ID from that card master appended to request, and then look into cardholder and its transaction and perform some analysis, and then we would do some mathematical transformation to prepare the data for statistical analysis, and then pass it into a fraud analyzer, and then fraud analyzer would finally give the response. Now, as we are increasing the rate of transactions, we will need to scale out the solution. And in the example that I showed when running the system, we had 2 partitions for each application. I would say this is coincidence that the number of partitions for each application matches. You can plan partitioning for each application separately, how many partitions. And so we split the authorization request load into 2 partitions, and then each partition can then send request to either of the 2 partitions in the next application in the chain, and then one of the final fraud analyzer partitions would send the authorization request to whoever sent the call in. So now that we have scaled for the load, we also want to plan for high availability. We don't want failures. As we saw, we managed to kill an instance machine. We have broken one of the shards for merchant master, and nothing bad should happen. And what should have happened is that this whole branch, the half of the flow would get corrupted or missing. That didn't happen because the second backup instance took over. And that's also possible to do with text platform. It's done simply by configuration. And so for each of the partition, in our demonstration, we had one backup instance. I would like to give overview of how the project is developed, how it looks in the code. So if I take the cardholder master application, which has the most, let's say, complicated state. So this is how you would develop, you would design the model, data model. There is an XML language, and you are basically writing an XML, and from this, there's a tool that will generate Java code. So this is integrated with the tool chain. So since we are using Maven, this is Maven project. This is going to be the code generation will run with the when running Maven build, and every time, for instance, if you are using IDs such as Eclipse, if you save this file and you have automatic build on, every time you save this file, it will update your Java objects that are generated, and then you can immediately use them in the code. So to see how cardholder master application looks like, the state is really simple. It looks like just a Java container such as a map or collection. But what we have here is the main method is handler for authorization requests. So what it would do is simulate some time spent on performing the fraud analysis, and then based on the result, it would then form a request that would be passed either to the fraud analyzer application, or it would be if we already detect fraud and we give it a high score for fraud, then we would return immediately. And Also, what I wanted to show is that whole thing with scaling and backup instances and everything is also done just through configuration. You're just creating instances of virtual machines, and with few configuration parameters, you can set up your replication and sharding and everything. It's there's very little coding involved in that. You are only focusing on your business logic. So if your model becomes bigger and bigger, we have demonstrated the rich model with merchant data, but let's say we are starting to adding ATM data if transaction is withdrawal from an ATM machine or anything else. Then when you are chaining up messages, the chain becomes longer and longer, and if that breaks your latency requirements, then you may want to have a different approach. So this is one of the approaches, is to kind of broadcast to other micro apps to call out that you want some data, and then each of the applications would return and give you back bits of data, and then you would put it all together and use that for analysis and then produce response. And normally this would be difficult if you have to handle timeouts, if something gets lost, if something fails, what would you do? But even this isn't complicated if you have guaranteed delivery. You know that everyone to whom you send a message will respond back and give you the bit that you need, and then you can continue processing. So that would be all that I have for demonstrating the project that we have.
Well, that was really good. Okay, so Igor, thank you for that. And we do have a couple of questions coming in. So just to let everybody know, we are going to save some time at the end to make sure we address all those. But quickly, Colin, do you mind kind of just touching on the durability and reliability pieces? Because there are a couple of questions about that. And I noticed that when he was showing those, that it looked like it was very durable, even though it said memory.
Yes. So let me take back control here. All right. Okay, can you all see my screen?
Yes, we can. Wait, no, I can't. It says waiting to view.
All right, let me try one more time here. All right, hopefully folks can see my screen again.
Nope.
Well, shucks. All right, any better?
Yes.
Yes.
Perfect, sorry about that. Your question was about sort of reliability. I know we've got questions coming, so I'll try to go through this sort of quickly, but one of the reasons why we can sustain such high throughputs while doing exactly once delivery is that the primary mechanism for achieving persistence, like Igor was showing, was to start and launch a backup instance of the application. So the way in which, as we're processing messages, all those state changes are replicated in a pipeline fashion to a hot backup. So We can do that extremely quickly with remote direct memory access, and we can do it in a pipeline fashion, so we don't have to wait for acknowledgement for that persistence before we start processing the next transaction. So really the key to how we can scale and stream so quickly is really memory-to-memory replication. Now, of course, the platform does allow you to persist to disk as well, but as long as you're protected by a backup instance, we don't need to actually sync to disks. So that also kind of improves throughput in cases where you might have less than the fastest disks. Another really key piece of the persistence architecture for the X platform is the ability to asynchronously siphon the transaction processing data into backend data warehouses. So Igor was talking about how we hold a year of transaction data in the credit card holder app, but you know, for regulatory reasons, you might need to hold on to that transaction data for a lot longer. So asynchronously, you can siphon that out to sort of backend data grids for longer retention or sort of much deeper analytical processing. I'm going to skip over this slide in the interest of time. Just one last reliability feature I'd like to talk about is we also, though we do memory-to-memory replication through application clustering within a data center, we also have features to prevent you know, full data center disasters. So like when we're running in Wall Street, for example, doing high-frequency trading, they're also pushing out all of that state and that whole stream of data to, you know, New Jersey. So from Manhattan to New Jersey, if something goes wrong, none of that data is lost. So definitely be happy to talk about that more in questions if they come up, but I do want to kind of keep us moving along. So Lynn, anything else I could talk about for you before we take questions?
No, why don't you just kind of go ahead and wrap us up, and then we will we'll move to questions.
Great. So I guess just to summarize, you know, why use X? I think it's a great way to introduce sort of hybrid transaction analytical processing into your business flow. It's so easy to get started with X that the barrier to entry is very low. It's simple to kind of try plugging an X application into your existing systems. Doesn't require any specialized hardware, and you don't really need a lot of infrastructure expertise to get started with X. So simple to get started, and it's very kind of easy to get integrated with other applications. You know, we support a lot of different message bus providers out of the box. Different encoding formats. We have tools to integrate with other data backends, so easy to ingest data from existing data store frameworks and easy to push data out. And like Igor was sort of mentioning or demoing, we have sort of monitoring tools that make it kind of easy to understand what your applications are doing. So I'd say, you know, it's very, very easy to get started. Worth taking a look at.
Great. Okay. So one of the questions that we have already gotten is where can I get to this? Here, we're going to show you a slide that has a couple of links on it now. And let me just explain that the first link is going to take you to the Getting Started guide. The second link is not yet active. As soon as we get off the webinar, I will work with Igor to get that into that GitHub link. So give us a little bit of time to get that one over there, but it will be over there so you can get to it. And that should take one of the questions off the table for those of you that have asked, or a couple of them actually, for those of you who have asked, how do I get to it? So Colin, we have another question that I will give to you, but let me just point out one of the questions that someone asked, is it open source? Yes, it is. There's open source and free source. Neve provides a support subscription, like most of the open source products that are out there, for if you need help getting started, or if you need support once you're into production. Then, so let me kind of start with this first question, if you don't mind. So Colin, the first question is, how easily can I integrate this platform with other tools that we already use? Is it an all or nothing? Can you talk about the components?
Yeah, good question. So the X platform, when you write an application, they are entirely self-contained in that we handle both the communication and persistence aspects of your application. But it's very easy to integrate with other data fabrics and other applications. So kind of by definition, because we espouse a multi-agent architecture, we're really all about sort of accepting streams of data and pushing data out. And in terms of integrating with other sort of data frameworks, we've got a rich set of tools for siphoning data out without impacting transaction processing. So yes, very, very easy to integrate.
Awesome. So the next question, Igor, if you don't mind, I'm going to throw a couple your way. Can you please tell us the technology stack that was used with this product or tool? And then the second part of that question is, what tools used for message stream processing and memory persistence, etc. So just a question about the stack in general.
If you are referring to the actual fraud detection, we use off-the-shelf solutions with Google TensorFlow and a few of our hand-coded check the naive Bayesian classifier, and then a lot of tweaking and fine-tuning and handling special cases. As for the technology stack, aside from our business logic, everything else is provided with X platform, so it's all built in, and so is the persistence.
Jump in there too. In terms of, since you ran this in our lab, it's probably more fair for me to. So we were using Solace as our messaging provider. So that's one of the message bindings that we support out of box. And in terms of the data framework, that's completely sort of native to the X platform. So I talked a bit about sort of the modeling tools, and Igor showed you about modeling the state. That is very much part of our replicated data store that's internal to the product. So working with state, all of the sort of machinery that does that extremely fast replication to a backup, it's built into the platform. So you could integrate with backend data tools. We're not doing that in this application. So sorry to interrupt you there, Igor. Maybe you have more to say.
No, that's on the point.
So another quick question here is, were there any speed mismatch between the microservices like the card master, merchant master, fraud analyzer? If so, how would you manage those?
There were actually, even as we were preparing for the demo, the process of tuning them was finding the bottleneck. And then once you find the bottleneck, you see, you can see where the messages are queuing up and accumulating in the message broker. And then this application that is accumulating unprocessed messages is a candidate for partitioning. And that's how we were partitioning one by one. If you partition those apps, then maybe some app that is in the message flow behind them would be the bottleneck, because now everything before it can handle even more traffic, and then this is then another candidate for partition until you tune it in a way that you don't see any application being a bottleneck. Another important component in this is the way you are developing the code. X platform itself is not creating garbage, so it doesn't trigger garbage collection. This may or may not be the case for your own business logic, but the X platform provides a lot of tools to avoid garbage collection. For instance, all that generated code, all those entities in the state provide specialized getters and setters that enable you to avoid creating garbage collection when you want to save something in an entity or obtain something and copy it further to send it to the next step, and so on.
That's great. Okay, thank you. So one quick last question that I have, and we're just a couple of minutes, hitting just a couple of minutes over. So for those of you that have time and want to finish up with the questions, that'd be great. So the last question that we got, Igor, was I noticed that you're using this in a cloud environment like AWS. Does it support other clouds and on-premise as well?
The system can be deployed on a Linux machine. So if you can run Linux, you can basically run this. There's no problems deploying it anywhere. And as far as the development goes, Colin can correct me if I'm wrong, but I think that development can be done on each of the three main platforms: Linux, Windows, and Mac. Code 41's choice development platform is Linux, but I think you can do development and run this demo that we will donate with on any platform.
Awesome. Okay, that kind of concludes our time for today. Appreciate everybody joining us, and the slides are attached in the handouts, but we will also be sending everybody a link to the recording as well as these updated. We'll let you know as soon as the demo source is posted in GitHub as well. Okay, thank you for your time today.
Thank you.